In this video, we're going to learn about Le Chatelier's principles in equilibria. So what is the basic idea behind Le Chatelier's principle? Essentially what it means is when a system at equilibrium, so a system's at equilibrium, is put under stress, the system will shift so as to relieve the stress and reestablish equilibrium. So essentially, if you have a system at equilibrium and you knock it out of equilibrium by stressing it, so that could be a variety of things we'll see later on. So you might, for example, add more reactant or remove reactant, or add more product or remove product. You might change the temperature, for example, or pressure. So those are all different things that you can do to knock a system out of equilibrium. When you do that, the system's going to act to basically counteract that. So if you've knocked a system out of equilibrium, the system will somehow react and proceed in a way that'll bring it back to a state of equilibrium. So let's take a look at some examples of that. In this video, we're going to take a look at a few factors that will knock a system out of equilibrium, and then we're going to take a look at how that system will try to adjust things to get back to equilibrium. So here we have a hypothetical example of a reaction. We have X gas, Y gas produces Z gas, and it's at equilibrium with our double arrows there, and then there's some heat produced, so that means we have an exothermic reaction. And we can disturb this equilibrium state. We can, for example, add more X. So what did we do? How did we stress the system out? Well, we added X. Okay, so how do we undo that? What we want to do is we want to undo that, essentially. We want to, if we added X, the system's mad because now we added more X than there should be. So we want to remove X. Okay, so if we add X, we basically want to do Control Z somehow, right? If you have a computer, Control Z is undo. Okay, it might be different on a Mac. I'm not sure about that. So how do we remove X? Well, the reaction can do two things. It can either go this way, left to right, or right to left. If you go left to right, you're going to use up X and make more Z. So one way to remove X is to go to the right. So when you go left to right, you're using up the excess X that you added. And then eventually your equilibrium can be readjusted. So basically what's happening here is that the shift occurs to use up the added species. Or if you remove something, to produce more of the removed species. So essentially, if I instead had removed X, then my system does not like that, so it wants to add more X. How does it do that? It would go from right to left to make more X, and then our equilibrium can be reestablished. So what would that look like on a graph? Here we have a graph, time versus concentration. And right now we're at equilibrium because the concentrations are no longer changing. They don't have to be equal, but the concentrations are no longer changing. And so I'm just going to make a little line over here to show what's happening when I make my change. So let's go with the scenario of we added some X. So if I added some X in, let's make this line a little bit longer here. If I added some X in, what I'm going to see is the level of X rise sharply. That's because I just added a bunch of X in. So it's not going to be a gradual rise like it's being produced over time. It's a sharp rise, so a nice vertical line to show that sharp rise. Now, the thing is, now that I've added that X, I want to get rid of it. Okay, I want to get rid of it. So how do I get rid of it? Well, I want my reaction to react with Y to make some Z. Because if my X reacts with Y, I get rid of the X as I make it, or that I've added. So essentially my reaction is going to go from left to right to reestablish equilibrium. So I'm going to see a decrease in X. I'm going to see a decrease in Y, and it's going to be a gradual decrease. But I'm going to see an increase in Z. It won't be a sharp increase because I didn't add Z to the container like I added X. It's just due to the reaction. So that's going to be a gradual increase in Z until, again, we've reached equilibrium and the concentrations no longer change. So we know we've reached equilibrium when the concentrations have essentially stopped changing for your reactants in your products because your rate of forward and reverse are equal. So essentially what happens is when you put in X, your forward is essentially going to speed up a bit to counteract the adding of the X, to remove some X. And eventually, though, you're going to reach a new state of equilibrium. You'll have the same K. This will not change K, so the K will be constant. It's just that you'll reach the equilibrium at slightly different concentrations, but the ratio will be the same. So if K was 50 before, it's going to be 50 again, just with different concentrations now since you've added some X in there. But the rates of the forward and the reverse will be the same at that point once you've reached equilibrium again. So sharp increase, that will lead the reaction to go towards the right to get rid of the X. So that means some of your Y has to decrease because you're using it up with your X. These two are reacting together. And then your Z would go up because you're producing a little bit more Z. And again, once we've reached the point where the concentration flatlines for all of them and no longer changes, so it looks like it was probably around over here. So this is, let's call it the old equilibrium. And this is the new equilibrium. But the K is still the same. Okay, so both Ks are the same there. And so if I were to remove, like I said, X instead, if you remove it, there'd be a sharp decrease. But then over time, we'd see the X go up again and the Y go up because the Z is being decomposed to make X and Y. So we're just basically acting in a way to oppose the change that we made. So that was our first factor that can stress a system at equilibrium. It's essentially changing the concentration. So this can be seen as a change in concentration of a reactant or a product. And so when you do that, if you increase the concentration of a reactant, you want to get rid of it. So your reaction would go towards the right. If you decrease the concentration of a reactant, you want to make more of it. So you'd go towards the left. If I added more Z, well, my system wants to get rid of the Z I added. So it's going to go towards the left to undo the Z that I've added. And so that was our first factor, essentially increasing or decreasing the concentration of products or reactants. And the system will act to either remove or use up some of the added stuff, the increased concentration, or produce some of the removed stuff, the decreased concentration, to bring the concentration back up until a new equilibrium is reached. In the next video, we're going to take a look at what happens when you change the temperature in an equilibrium system.